Now we're going to show how this works out with a numerical example. We consider a triangle with dimensions, with legs x, with equal legs that we call x. Okay, it's a 45, 45, 90 triangle. Its area is 1/2 x squared, as you well know. We're going to let y stand for the area. So y is 1/2 x squared, and dy, our uncertainty in y, we're going to interpret dy as the uncertainty in y, dx is the uncertainty in x, according to this equation, is dy equals x dx. Okay, let's say that you measure this triangle, and you've measured triangles to assess uncertainties. You measure this triangle and find that x is 15.0 centimeters d, plus or minus 0.5 centimeter d, and this is your measurement, and this is your estimate of your uncertainty based on how well you think you're reading your instrument, your measuring device. So again, x is 15.0 centimeters d, and in class I didn't put the d's on these centimeters. I did over here. I just didn't think that clearly over here. Now, okay, x is 15.0 centimeters d, dx is 0.5 centimeters d. Dy, as we said, is the uncertainty in y, which is the area. Okay, dy equals x dx, that's 15 centimeters multiplied by 0.5 centimeters, 15 centimeters d multiplied by 0.5 centimeters d, or 7.5 centimeters d squared. So there's your uncertainty in the area due to the uncertainty 0.5 centimeters d in the measurement of x. Now what's the area? Well, it's 1/2 times 15 centimeters squared, which is 113 centimeters d squared. There's another d I'm missing. Okay, we talked in class how this is 3 significant figures, and it makes no sense to express this to more than 3 significant figures. So we take the 112.5 that we get when we take half of the square of 15.0 and round it to 113. It would be meaningless to call this 112.5. The uncertainty is 7.5 centimeter d squared. So we say that the area is 113 centimeter d squared plus or minus 7.5 centimeter d squared. The percent uncertainty then is what? Well, the uncertainty divided by the area, and that comes out approximately 7%. Little less, I think, yeah, that's 1 part in 15, that's 1 part in less than 15. So, yeah. So it's a little less than 7%, but we're rounding it to 7%. And when we do error estimates, we always round a little bit high. We never want to underestimate our errors. So if there's a round off involved, we round high. Okay, 15 centimeters d minus 0.5 centimeters d is less than or equal to x, less than or equal to 15 centimeter d plus 0.5 centimeter d. What's this express? Excuse me, I got a cough. This simply expresses the fact that x lies between 0.5 centimeter d, your uncertainty, beneath or less than 15 centimeter d, your measurement, so that your actual side of the triangle is between this and 15 centimeter d plus 0.5 centimeter d. And that can be written numerically 14.5 centimeter d less than or equal to x, less than or equal to 15.5 centimeter d. And if we square these now, remembering that we've only got 3 significant figures here, and we're going to kind of round the uncertainty anyway, to the nearest whole number, we have something very much like 210 centimeter d squared, less than or equal to x squared, less than 240 centimeter d squared. Just squaring these 3 quantities, which means that our area is going to be between 1/2 of this quantity and 1/2 of this quantity, which means that the area is, and you can work out, you can divide this by 2, you can divide this by 2, you get 105, 120, and to the nearest whole number, well, it's 113 centimeter d plus or minus 7.5 centimeter d. That's a way of expressing this inequality, meaning that the percent uncertainty is 7.5 centimeter d over 113 centimeter d, or times 100%, and that's, again, approximately equal to 7%. This calculation is somewhat less trouble than this calculation, and it's more general. It has a greater degree of applicability. But this method and this method give you the same thing, so that this should make this very tangible. Now, the uncertainty in x is 3 1/3%. Now, how do we get that? Well, we divide the 0.5 centimeter d by the 15.0 centimeter d, excuse me, and express that as a percent. The uncertainty in the area should be double the uncertainty in the side. And if we multiply 3 1/3% by 2, we get 6 2/3%, which is close to 7%. And remember that this actual division gives us something a little less than 7%. Now, these two results aren't going to be exact. If we double the uncertainty in x, it's not going to be exactly equal to the uncertainty we get in a. And that comes back to the fact that in doing this approximation, we've neglected the dx squared term. Remember that term from before? And in this case, the uncertainties are fairly large. Okay, uncertainty of 3% or 7% is larger than the uncertainties we'd prefer to be working with, but we do sometimes work with fairly large uncertainties. So dx squared isn't quite as negligible as it would be with smaller uncertainties like 0.5% or even 1%.